Okay, folks, here's yet another bit of knowledge. I am recording for you from my COVID-19 bunker. So I'm going to talk about climate change again, this time talking more about the science behind it, not just looking at our public perceptions and kind of general thoughts about it, but really getting into what it is. How do we know it's happening? The evidence, the fact that's telling us what's going on and how we get it. So I'm going to talk a little bit about climate. I'm not going to dwell too much on natural climate change. It exists. I'll point out some, kind of obvious, basic facts just to kind of dispel this myth that what we're seeing now is perfectly natural and normal and what the Earth does, because that's not the case. And then, we'll spend most of the time talking about the actual greenhouse effect, how the planet is, in fact, warming, and, what that means for our future. And sadly, as we'll see, what I'll discuss is, stuff like some of these things that I talk about, they were predictions in the, distant future when they first arose. Right, and now it's actually a case of, it's happening. A lot of the stuff is either become true already, or we're starting to see it shift, or whatever. And so we'll get into that. And I have the picture here on the screen of California, which seems to be perpetually on the fire all over the place. And that's just that's an example of this stuff where we're seeing these things that, happened. Wildfire is nothing new in a place like California. And you can think about our climate, right? What kind of climate is most of California? What kind of climate region does most of California fit into? Yeah, I'll wait. Don't even put your hands up. Just shout it out, right? Yeah, Mediterranean climate, right? Remember from the lecture on the Köppen climate regions that we have, that CSA to CSB classification, that's California. We normally speaking don't get water coming in the summer months because of our location on the west coast at our specific latitude, the proper perfect conditions out there in the Pacific Ocean and all that. We have a very dry summer, and that has just lent California to catching fire every summer. That happens, right? But things are getting worse. We're seeing more severe stuff. Some of that is clearly because we are also growing in size. We're pushing houses out into the forest, getting more people living out there, bringing more electricity and just civilization out into more natural environments, and that's going to lead to accidents happening. Some of it is the fact that our fire policies have not been the best, that we should take a more proactive approach in managing forests, not just leaving them alone and keeping them from catching fire, but actually making sure we're thinning certain areas so that if it does catch fire, it doesn't get out of control right away, right? But also, a big reality here is the fact that California has been seeing more, cases of drought year after year. We talked about that before the shift to online stuff. We talked about, the fact that we haven't really left the drought that we had starting at the beginning of the century. That even back in like 2011, we saw those drought maps. We saw that California was looking pretty good, but wait a month and the drought comes right back. Right, so we just haven't had water coming in, and a big part of that, as we saw, is that it has to do with anthropogenic climate change. All right, and we went over that term, anthropogenic. So anthropos means humans, humanity, people. Genic effectively means caused by, created by, creation. So that's what we're dealing with here, right? Human-caused climate change, human-caused warming, to be contrasted with the natural stuff. So we're going to get into all this stuff. It's not going to be the most chipper thing. Not the most exciting, but something we got to talk about, even in the face of all this, scary coronavirus stuff as well. I'll try to make it not as depressing as possible. I don't know, maybe post a link to some kitten videos or something like that at the end. All right, so let's get into it. Let's get into this natural stuff to start with. Climate, as we've discussed, is a pattern, right? So we're looking at weather data long term. So we, gather temperature. We look at, precipitation amounts and when it falls and stuff like that. So we're looking for a pattern. What a place is like in the summer, in the winter. How much precipitation does it see year round, and so on. But if we look at it long enough, we see that all climate changes given enough time. All right, and that's perfectly natural. That has taken place before humans even existed. This picture on the screen is a perfect example of that. We'll be talking about glacial activity later, but this is up in the northern Sierra Nevada mountains, far away from any currently existing glacier. But on the rock, you can see how it's been scooped out. You can see the lines in there. Those are glacial striations. That's glacial ice moving over this rock, gouging it out with other bits of rock that it's picked up, eroding this material, and scooping it out in this way. So this rock looks the way it does because of glacial ice, because of a massive amount of glacial ice that covered, this whole area. But, that was 1 million years ago, roughly. This is taking place back during the Pleistocene epoch. We are long since, out of this last great ice age. So clearly, climate has changed. And again, clearly it changed with, no human influence whatsoever. Right? Actual Homo sapiens didn't even exist when this stuff is being carved out. So sure, absolutely, climate changes naturally. All right? But, we today speak of anthropogenic warming, anthropogenic change. And the idea is that we're saying it's not natural, right? It's human caused. And the evidence for this, a lot of this comes from the fact that we are studying paleoclimates, right? This concept of paleoclimatology, it's the idea of past prehistoric climates, right? So like just paleontology in general, we think of people, digging up dinosaur fossils and those kinds of things. We have other scientists who are not so much interested in the fossils, the organisms themselves, but they're looking at, what was the whole planet like at this time? What was the climate like? And I will briefly, I think I have some slides in here about how we do that. But based on these past climates, what we've been able to reproduce, what we've been able to figure out is that we can look at that trend that's going on, right? We can get a sense of how has it changed over time, and then we can look at what's happening today. So like this graph right here is showing, effectively, just simply speaking, what temperatures are doing. Okay, so the higher the line on the graph, the warmer the temperatures, and it's saying less ice, right? Meaning that as temperatures warm, this glacial ice is going to melt. That's going to run out into the oceans. We're going to have higher sea levels. We talked about that with used to see and that concept of where water is, right? We have, same amount of water on the planet all the time. For the last 2 billion years, we've had a constant amount of water. Now, we're at a point where or because of that, we're at a point where we can map and study and see how, changes in sea level that is affected by temperature. And that says something about glacial ice and so on, right? So that's what we're looking at here. And if you go back, tens of millions of years ago, you can see that like 60 million years ago, it's a lot warmer back then. And we see this general cooling trend, right? And let me see. I think I can do this. Let's try a pen. Let's see if this works. Except it's going to be red. Hold on. Concern it. Let me see. Discard. Oh, crud. All right, I know this looks like Grandpa using technology, but hold on. Let me see if I can. Here we go. Let's use yellow right here. So when we're looking at this stuff, I'm sure this will work. When we're looking at this stuff, we're not so much interested. Like you see this thing right here, this little, spike that goes on. That's interesting. You could study that, get a sense of what's, happening there in that specific moment. We see this rapid drop right here. That is interesting for a simple moment in time. But honestly, when we're looking at the big picture, when we're doing this climatology, whether it's looking at the paleo stuff or what's happening today or whatever, when we're looking at that big picture, we're not following these lines, up and down completely. Like all these jagged things here, we're not going up and down with it. What we want to look for are trends, right? So to just because this is easy to start from here to here, rather than getting fixated on the up and down, we would instead draw a line. Let's see how I can do this. Oh, that's gorgeous. So we would draw a line more or less through the middle of this stuff to get a sense of that overall trend, right? And so if we look at that, we can see, make it like an arrow, in that direction, it's going down, right? We're seeing a cooling trend. And actually, if we go back, all the way here, we have this warming period up until about 50 million years ago. But when we look at that overall trend, when we go from here at 50 million years ago to here, we can see, I don't have a mouse. I'm just doing this with my big, fat, stupid fingers. Hold on. If we look at that yellow line, we get a sense of overall, there's a cooling trend, right? The planet should be cooling, right? Even though we've left the ice age, we've had this little warming period, but we should actually, still be going into this overall cooling period. We shouldn't see this rapid, incredible warming that's taking place. So that, if nothing else, what this shows us is that what we're seeing doesn't fit with the overall natural trend, right? That's the concern. That's what we're talking about when we say this whole natural thing. Yeah, it's good to know, but that's not what we're faced with, and that's not what we got to figure out. Okay, so that's the idea there. Looking at more contemporary stuff, this is a map showing the rate of change we go from 79 to 2005 in degrees Celsius per decade. Effectively, what we're looking at here is the red means it's warming, and the darker the shade of red means it's warming more. White means really no change is taking place, and blue means it's cooling, right? And again, the darker the blue, the more the cooling is taking place. And just looking at the map, you can see overall, we've got more red than we do white or blue. So clearly, the temperature is warming, right? And has been doing that for a while now, right? For decades now. We're seeing that we are increasing in temperature. One of the frustrating things is that it has not been a constant, warming everywhere. You can see in the southern hemisphere, we have cooling taking place. In the northern, we have this warming taking place. It's, kind of unfortunate that it's not a simple, straightforward bit of warming that's taking place, because skeptics, people who want to either, just cause trouble or to profit off of, pushing this narrative that nothing is happening, they'll look at this and say, see, it's not even warming consistently. You don't even know what's going on. You're calling it global warming, but some places it's global cooling or whatever, which is nonsense. What it's showing, and what this really should be making us all think about, is the fact that, oh my God, it is, that red in a place like Greenland up here, this very dark red, that's not a good thing, because what is Greenland covered in? A massive ice sheet, right? It's all this glacial ice up here, and so as that warms more and more, it's still cold, and compared to whatever we would experience down here in Southern California, which, hey, not too bad. We're kind of just on the border right here. But here, it's a problem when we have that water melting, and then that ice melting and turning to meltwater and heading out into the ocean and helping ocean levels go up and all of that. All right, so this is of great concern, and we'll see more charts and stuff like that. And the idea, again, is to look at this stuff and get that big picture, right? Rather than focusing on the fact that, okay, we've got some darkish blue down here, so it's not a big deal. No, we want to look at that overall thing and also acknowledge the complexity at work that you can have, like here in, California and down into Mexico. We have areas of cooling, areas of no change, areas of warming. It's a complex scenario, what we're faced with. And again, all the more reason to take it seriously and to actually work through it and figure out what's happening and what does this mean for us. Okay, so in fact, here we go. Back to this idea of the last ice age. Not going to dwell on it all that much, but we have geologic time, right, which is the way in which geologists have tried to make sense of these incredible, vast amounts of time. I know I've mentioned this to at least some of my students this semester. How old is the Earth? I'm waiting. Put your hands in. Just shout it out. Right, perfect, class. 4.6 billion years old. That's a huge amount of time, right? We'll talk about that later when I get to geologic stuff, and we talk about this concept of geologic time in more depth. But that's just, it's hard to grasp with our tiny little brains and our tiny little lifespans and all of that, right? Like, we're lucky if we can make it to 100 years old. That's a massive lifetime for us. And you can see just with these numbers here, that's nothing compared to how long the Earth has been here, let alone the more recent changes that have taken place. All right, so we break stuff up into eons and eras and periods and epochs and these different units of time. And it simply is referring to a change in life or something around the planet. All right, so we have the Pleistocene epoch, which roughly takes place from about 1.65 million to 10,000 years ago. Okay? And then after that, that's when the planet starts to leave this ice age. It starts to warm, a little bit here to not have as much glacial ice everywhere, but it's still nowhere near like it was, say, 50 million years ago. And so as we leave that ice age, we go into the Holocene epoch, all right, which is just means we're now out of that ice age. And traditionally, this has also been linked to the idea that humans really start to take off here. Now, as temperatures warm up a little bit, humans have also, figured out things like technology, better weapons and fire and clothing and just stuff in general. We're figuring out stuff to make life easier. So this is really when humans start to spread all over the world. It happened in some places even sooner than this, but we really see stuff take off. So we call this the Holocene epoch. There's also a push, I don't have it in here, no, I've written about it. You guys should have heard this by now. But we have what's also called the Anthropocene. Right? So again, anthropos, meaning, human. So we're looking at this new epoch of the Anthropocene, which is really saying that, look, we're out of this Holocene. We're now in a moment where humans, not only are we everywhere, but we're actively changing the planet, right? The Anthropocene acknowledges climate change, the fact that we humans have radically shifted how life on this planet works. So it's worthy of a new moment in time. And of course, geologists move incredibly slow with this stuff. It's not an official part of the geologic record right now, but it may be. But it serves a useful kind of way to frame what's happening, a useful way to think about this new reality in which we live. All right, well, and we'll maybe talk about that stuff in more depth later on. Okay, but that's just what some of these terms refer to. Yeah, we had glaciers. Look, let's move on. Let's get to the good stuff about what's in it for us and all that. So we're not going to talk about the Ice Age so much. But it is, as I mentioned this before, it is worth at least acknowledging how we know some of this stuff and get a sense of what's going on, right? So in some cases, we just see activity of glaciers in places where there aren't glaciers today. We'll cover that stuff later on. We get into how glaciers actually form and work, what they do in terms of erosion and deposition. But, we can look at that stuff, but we can also study some other things. This is a pretty remarkable field of study. It's been growing rapidly because people need to, get a sense of these past climates. There's a lot of, work to be done so we can get a better handle on what's happening today and what is normal. And so, one really great way to study past climate is through ice cores, right? Drilling into like that Greenland ice sheet, digging down in there, pulling up these cores. And so it's the idea you can kind of see the stuff in here. You have the drill rig that's working its way down, and it's got a hollow drill bit, right? So it digs down into the ice and pulls up this cylinder of ice. And this is all marked and recorded, not only where it came from, but where these different depths are, so we get a sense of where this ice is actually coming from the glacier itself. And so we pull this stuff out and we can study the ice, right? We can actually look at it. One cool thing about, get it cool. One interesting thing about this is that with glacial ice, as it forms, what happens is it's snow that accumulates year after year. And as more snow builds up in this area, there's a lot of pressure. It actually recrystallizes. So the snow actually transforms into something new. So it's still, we're still dealing with H2O, but it's not just water freezing. It's this transformation process. That's what makes glacial ice. And in this process, sometimes we have little bubbles in there, little pockets of air, of the atmosphere that get trapped in the ice. So not only can we see, just conditions in terms of how cold it was or not cold it was, and how these different layers of ice have formed over the years. It's kind of like tree rings, but we can also extract little bits of atmosphere from, thousands and thousands of years ago and get a sense of what was in the air. One really cool thing is up in Greenland, there's been evidence of lead found from the Roman Empire, right? So as the Romans are growing and building and developing stuff, they're using lead in their plumbing. Just not a good move, but that's for another discussion for another time. But they use a lot of this stuff, and so as they're growing, because this empire is massive, they're kicking up a lot of lead dust effectively. That goes up into the air, swirls around in the upper reaches of the atmosphere. Some of that winds up in Greenland, right? And so it gets actually compressed into the ice. And that right there kind of goes to show how powerful we humans can be, where you think of something as, they were impressive for their time, but still pretty primitive compared to modern industrial society. But if you think the Romans could actually have, their pollution wind up in Greenland, kind of goes to show how powerful we humans can be. All right, but we see this in the ice itself. So that's one way in which we record that. Actual dendrochronology, which is literally, it's talking about tree ring, analysis to record, to study time and the conditions in the past. We do that. It's a little picture of pollen under a microscope, all sorts of things that are being studied. And, you think pollen, that's coming from a plant. If we see what kinds of plants existed, however many thousands or millions of years ago, we get a sense of what the climate was like, right? What were the temperatures? What was the precipitation? That kind of stuff. So there's a lot of this. There's, lake sediment. People are digging down. If you're able to see even that Nova thing I mentioned last time, they're spending time in, Belize and the Caribbean in general, pulling up sediment, getting a sense of how powerful these storms were based on the stuff that was blown around, right? These are brilliant ways in which we can kind of indirectly get a sense of what was happening at a time when we weren't there, or we didn't have the technology to really study it or measure it or whatever, right? That's what we're doing, to study this past stuff. And then, I mean, well, this is kind of cool. We can talk about it. Again, with all of this study of paleoclimatology, we see that the climate has been radically different in some places. These are some kind of rough Landsat images and remote sensing images of Egypt, the Sahara Desert in general. I forget exactly where this one is from, but throughout northern Africa, where we have this incredibly massive desert, this very dry place, these two images released by NASA are showing, the top one is showing it's, desert, right? It's kind of this, the colors in here don't get taken by them. We'll see a lot of false color imagery, and it has to do with different types of, it's not even, pictures isn't the right term, but images that we take. Not every satellite image is simply a camera up in space taking a picture as we'd think about it. There are other ways to take these pictures, and some of these different colors, it's referring to the different spectrum, how things are I guess reflecting these different colors basically, and that can tell us a lot, right? In this case, not so important. So it's simply, this is what it looks like from the surface, more or less. But if we use this synthetic aperture radar, effectively this ground penetrating radar, you can see these little fossilized river channels in here. This used to be a very different environment. It was wet. There was water everywhere. There were shallow seas in this area. In fact, you even find, in places like Egypt, you'll find fossilized mangrove roots, right? We saw this picture before, this one taken from Key West in a very, wet, lush environment. You see these things, they existed a while ago, millions of years ago, in what is, today, this incredibly dry area, right? And so this is what Northern Africa would have looked like if we go back like 50, 100 million years, whatever the actual time frame is. You even find, in Egypt, you'll find whale fossils, right? The idea, I think, was that this was a shallow sea area. Whales would come in to, give birth or whatever, and then, head back out into deeper waters. So we see this stuff here. And it all has to do with changes in, these climate things that we talked about, like the ITCZ, okay, which is today where this air comes together, converges, gets pushed up, and then rain comes down, right? So that is more or less around, the equator today. But in the past, when we had these whales in the shallow sea here in northern Africa, this was further north. Okay, so this, where we have all this precipitation falling, was much further north. That means the subtropical high pressure cell was also further north. Things would have changed. What we think of as normal today wasn't normal, wasn't the way it was if we go back hundreds of millions of years. Okay, and a lot of this, to explain how this stuff works, it's based on the work of this guy Milankovitch, who was brilliant. And apparently, the way I've heard it is that this guy was this mathematical genius and was able to calculate all this stuff. And it wasn't until we actually developed computers to the point that we have them today, that we're able to check his work and see that, oh yeah, he actually was perfectly correct in this. But he's looking at all this stuff we talked about a month or two ago, whenever it was, about the sun and the earth and our seasons and our revolution around and all that stuff. All those numbers and values and the way it works that I gave you before, that's absolutely true within our lifetimes, right? That we have this plane of the ecliptic, this oval shape in which we revolve. See, I did it too. Revolve around the sun, right? That's happening for us now. But Milankovitch figured out that, actually, if you go back far enough, it was more circular, right, than this more oval shape that we have today. So it fluctuates back and forth, roughly about 108,000 years to go, between the circle to the oval and back to the circle, right? So it means in our human lifetimes, we're not going to see these changes. But over time, given enough time, that's going to affect stuff, right? And don't worry, I'm not going to test you on these exact numbers here. They're not really important, but I think it's useful to get a sense of how this stuff changes. So we have that. Our axis wobbles a little bit. It's the idea like when you spin a top and it's going and then it starts to lose that momentum and it starts to wobble. We do that. And it doesn't mean we're going to topple over and, spill out into space or whatever. But every 26,000 years or so, we kind of wobble. We're a little unsteady, right? Our tilt, as you recall, is 23.5 degrees off of perpendicular from the plane of the ecliptic. Well, we're at 23.5 degrees now, but it fluctuates between about 22 to 24 degrees roughly every 41,000 years. Now, what all this means is that over long periods of time, we're going to see this natural climate fluctuation, right? And it had like our tilt. We got into how important that is for the subsolar point and where the Tropic of Cancer and Tropic of Capricorn are and the Arctic Circle and all that stuff. If our tilt isn't at 23.5 degrees, but is actually 22 degrees, that's going to change everything, right? Where these different key locations are. That's how we get stuff like the ITCZ a little further north, right? So that's changing climate in this natural sense. And when you put it all together, we get these fluctuations that are going on. This is what's called the Milankovitch curve, where it's just this idea of, in the grand scheme of things, in, time frames that are way bigger than any human lifetime, we see the Earth go through these natural warming and cooling cycles. This helps to explain stuff like ice ages and warming periods and all that stuff before we humans actually show up. Okay, that's the idea there. And this kind of gets back to, again, that whole natural thing. This is what people are talking about when they say that the Earth naturally changes. The key difference, though, is that honestly, this stuff doesn't, naturally change within human lifetimes. It's not some rapid shift, right? That's a key thing to be aware of here. All right, that's enough with this natural stuff. Let's get into what we humans are doing, shall we? Because that's the important thing, and to get a sense of what does that mean for our foreseeable future. All right, so to fully understand this, let's get into the sun's radiation coming to Earth. We'll talk about the greenhouse effect. We'll get into, what that is, and then we'll see how we're affecting that. All right, so we've already discussed this before, but our insolation basics, again, incoming solar radiation basics, are that we get shortwave energy in from the sun. Okay, so this goes back to that whole electromagnetic spectrum we talked about. Wavelength is just how, close together or far apart these energy waves are. So the stuff we're getting in is shortwave energy, and then we're also emitting longwave energy, right? And it's the same energy in the sense that it's coming from the sun, comes down to the planet. We absorb some of that, whether it's, the surface of the planet, if it's organisms, like whatever it might be on the planet, this energy is absorbed, and in that process, it's converted to long-wave energy. Okay? And with all of this, the energy that's coming in, we're not keeping it, right? So we have shortwave energy coming in, but we also need to get rid of an equal amount of that energy. We can't just keep taking in energy, or the planet would, melt or explode or whatever. Right? So it's this constant process of stuff coming in, stuff going out. And that's what diagrams like this are trying to show. So you see this shortwave energy coming in from the sun, right? And so some of that is immediately reflected and sent back out into space. Okay, this concept of albedo I'll talk about in a bit. But the shortwave stuff comes down, shoots back out. Great, we don't have to worry about that. Other stuff comes down here, to the Earth itself. Again, some of that can be reflected, but other stuff will be absorbed in some way. And so that's what this long wave stuff is. It's converting, the shortwave stuff into this heat and then sending that long wave stuff back out into space. This fantastic diagram. I've never even read the whole thing. It's complete garbage. It terrifies students. And to be honest, most professors look at this and go, yeah, way too much going on. But what we're getting from this, why I keep this in here, is the idea that we have, 144 energy units, whatever that means, right? Gained by the surface, and then 144 energy units lost from the surface. Everything coming in has to go out, right? And you can see that here. Same numbers in here. It's showing that, we're not holding on to anything for too long of a period. Eventually, anything coming in is going to go out, right? And so albedo is one really easy way to get rid of energy right off the bat. So albedo refers to how reflective something is, and we express it it's a percentage. This is a little too mathy. What it's really saying is that we have an albedo of 90% if we're dealing with ice with snow, right? So the sun, it's sending its radiation down, so we have 100% of that comes down, 90% is reflected, and only 10% winds up getting absorbed, right? And typically the rule is the lighter the color, the greater the albedo, right? The more is actually reflected. So ice with snow, very white, very light in color, 90% albedo. Bare ice, which can actually have a lot more blues in it, has an albedo of roughly 50%, where half of that will be reflected, half of that energy will be absorbed, and then open ocean, that darker blue, has an albedo of about 6%, meaning 94% of this energy is absorbed into the ocean itself, right? And so this gets into that whole concern we have with ice melting. It's means that our albedo lessens, and it's this, snowball effect, so to speak, or what's often called a positive feedback loop. But it's the idea of, as we have more ice melt and snow melt and all of that, the albedo lessens, which actually, causes more of this energy to be absorbed, which warms everything, which causes more of this ice to melt, which means we have more open ocean, which means we're taking in more stuff, and we just get hotter and hotter as this continues, right? The pattern just keeps going, right? That's the concern. And this is showing other stuff that exists. So like, asphalt, paved streets, 5 to 10%. That's why it's so hot when, in the middle of the summer, you're walking out to your car in the parking lot. It's because it's a dark surface. So it's absorbing a lot more of that solar energy, right? And so roughly our albedo is about 30%, meaning of all this solar radiation that's coming down, we're already just immediately getting rid of 30% of it, right? That's the general idea. So that's how that works, okay? But with the greenhouse effect, what that's doing is it's referencing this other stuff, right? That 70% of the energy that's being absorbed. Okay, so we have the sun shining down right here. Again, the yellow, the convention here, yellow is showing this shortwave energy. This is showing the albedo right here. So, that 30% is heading back out into space, and the shortwave radiation can easily pass through greenhouse gases. Okay? And they're simply called greenhouse gases because they contribute to this greenhouse effect. The most famous one we discuss is CO2, carbon dioxide. Methane is another big one that we've kind of slowly figured out is, that's also a concern. But what these gases do, and remember, CO2, it's a tiny portion of the greater atmosphere, but what it's able to do is it's actually able to trap and delay the release of this long wave energy. So the short wave stuff can pass through no problem. The longer wave stuff gets hung up with these greenhouse gases, and it'll actually get pushed back down to space, and it'll kind of bounce back up, and eventually all this stuff gets out of here. But it's keeping some of that heat down here at the surface for longer. Okay? And that's great. That's a natural thing, and we want that. You can think of the greenhouse gas as a nice little blanket over the planet. It keeps some of this heat here so that we humans can exist. If we didn't have it, it'd be a much colder planet. So we want this. This is a good natural thing. It's existed, before the Industrial Revolution. So that's perfectly fine. The problem is we keep putting more CO2 into the atmosphere. So this little nice blanket we have, this greenhouse layer right here, what was a nice blanket is getting thicker and thicker, right? We're getting hotter and hotter because it's harder for this heat to escape out into space. So as we continue to, primarily it's the burning of fossil fuels through coal, gas in our car, natural gas at home, like whatever it is. And some of the stuff is dirtier than other stuff, but still, this is all contributing to carbon dioxide going up into the atmosphere. As we continue to do that, we're making our blanket thicker. Our temperatures are warming, right? That's the greenhouse effect. That's global warming. It's a very simple, straightforward concept just right there. And you can see if you start to, dig a little deeper into this, you can see stuff can be a little more complicated. There, not all greenhouse gases are the same, and there can be different things in the atmosphere that contribute to it. But the general concept is the greenhouse effect refers to a blanket. I mean, the greenhouse, that's the analogy, right? Like a greenhouse where you grow plants and stuff like that. My little brain, it works with blanket. That makes more sense to me, right? So we have this blanket over us and we're making it thicker and thicker, and therefore we're warming more and more. Okay? And we see there's no denying this. This isn't one of those things where the science isn't, quite in on it or whatever. We know. We've seen correlations between these things, the temperature and the presence of greenhouse gases. Now, looking at these charts here, you can see that, the timeline here is thousands of years before present, right? So clearly, as I've said, this is when, humans actually show up around this time, modern humans. So clearly, if we go back in the past, not every single, instance where temperatures have gone up and we've had more, methane and CO2 and stuff like that has been connected to, human activity through, fossil fuel burning and stuff like that. But we are seeing that we are increasing temperatures, again, in this time where, cooling should be taking place overall. We're putting this stuff into the atmosphere at an alarming rate. All right. And it should be no surprise when you just think about the enormity of, human industry and, transportation and manufacturing and stuff like that. We're putting a lot of this stuff up into the air, and therefore we're warming temperatures at a rate that we just have not seen in human lifetimes, right? That's the real issue here. And here's a chart showing this stuff, the CO2 increase. This is kind of, an after World War II for roughly 50 years here. You can just see it's going up every year. And this zigzag has to do with different parts of the year. Basically, it goes down when it's summer and spring in the northern hemisphere. We have plants out with, full leaves, and they're sucking in that CO2. And then it spikes up a little bit, the upper part of that sawtooth thing, when we have, winter. And all our plants lose their leaves, and therefore they're not taking in that CO2. So we have those natural little, fluctuations. But again, that overall trend, if we draw our line, I'm not going to draw anymore, but you get the idea, is it's going up, right? So we're pumping a lot more stuff like this into the atmosphere. We're making that blanket thicker. Now, to add to some of the complexities here, not every place is going to warm at the exact same rate, or even warm at all, right? Like that map I showed earlier. It's not a consistent thing. And so this chart is showing where these changes are going to be taking place and by how much, right? And this kind of goes back to that issue of mega climate that I spoke about before, where, when we say stuff like 2 degrees Celsius worldwide, you have to remember that is worldwide. We're averaging out stuff. For this, enormous planet on which we live. But when we look locally, we can see, like at the equator, we're not anticipating that much change in terms of temperature. There could be other stuff that goes on, but in terms of temperature, not that different. As we go here into the northern hemisphere, so 30 degrees north, remember we're at about 34 degrees north in LA in the Antelope Valley, specifically. So as we, that would be roughly here, maybe a degree and a half, something like that. We can expect that. It actually goes down as you go up a little bit. And then this, of course, is that alarming change that we're seeing and what we're expecting to continue to see, right? And honestly, a degree or two for us in Southern California, that alone isn't a terrifying thing. When you start to see things like, 6 degrees difference in the Arctic, that can be the difference between, ice staying frozen and ice melting, right? And, flowing into the oceans and rising sea levels and all that stuff. Down in the southern hemisphere, in the Antarctic, not quite the same. And there are different hypotheses about that. Scientists are still trying to figure out exactly what's going on. As far as I can tell, there hasn't been a definitive, proven hypothesis to explain it. Just my speculation as a researching climate scientist would be it's probably something to do with the fact that we have way more land mass in the northern hemisphere, way less land mass in the southern hemisphere. If you look at a map of the world, you can see, like Africa and South America, they get skinny as you go further south. You don't have a big mass like Asia and Europe or, even North America in the southern hemisphere. So you have different, ocean currents and just stuff like that, right? So that is most likely why we see some of these changes. But again, people are studying this stuff still. We're still trying to figure out those definitive reasons why. But we are seeing, this isn't even a prediction anymore. We're starting to see that these changes are definitely happening. All right. And here's an example of this. Now, this map, it's 4 years old. I pulled it for a specific reason, but you can go to NASA, to their website. You can find maps like this every year. They continue. It's the same stuff. It's continuing to warm. So again, we see that issue of down here in the southern hemisphere, it's actually cooling, right? So this anomaly stuff is where we see a general, cooling trend. And the red, the dark red especially, is where we see a warming trend. Okay? What's also terrifying, if you look at the scale, here you see it's not equal on either side. It maxes out at 12.9. And whereas this purple color, I don't even see any on here. So it'd be like, a -4 is what we're dealing with right here. So definitely the warming is even more intense in terms of an anomaly, right? We're comparing what it was in January 2016 to this average going from 1951 to 1980. Okay, so we're definitely seeing this warming taking place in the Arctic. A few, again, weird spots, little things taking place. It doesn't mean that this warming isn't happening though, right? So this is, again, also why we say climate change more than global warming, because you say global warming and small-minded people get all, freaked out about, well, it's not always warming, right? No, it's changing. So perfect. There you go. But then down here, off of the coast of, Peru and Ecuador, in South America, this warming that's taking place here, that's actually El Nino at work, which is, as I think I mentioned before to at least some classes, El Nino, it's a short-term natural climate fluctuation. It's where this side of the Pacific Ocean warms. We don't really know why. We just know it does happen. It's called El Nino based on little baby Jesus. It was the idea that like Peruvian fishermen noticed that it happened around the time of Christmas. And so it's named, it's named baby Jesus, basically is what, El Nino is referring to. All right. So when this warms here, it's this oscillation that's taking place. It's warmer here, cooler on the other side of the Pacific, which is where wind up over here, right? Because we're going around the Pacific, winding up over here near, Indonesia and Australia, this part of the world. They cool off. And what happens is we get a lot more rainfall on our side of the Pacific. They have drought, right? So it switches the normal thing. So this is showing, what I like about this January map is it's showing that, this is the anthropogenic stuff that we're concerned with. We also have the natural stuff at work. We also see that it's not consistently warming or cooling, from a latitude standpoint. There's a lot going on, and this goes to show why it is this complex thing that we do need to continue to study and to figure out, and it's why it's so frustrating when people are so quick to dismiss it. Honestly, a lot of people, if they're not just flat out lying, when they dismiss this stuff about global warming happening or climate change happening, it's because they haven't taken the time to really try to figure it out, right? It's too complex for them, and they just give up and say, it's probably a hoax or whatever. No, this is happening. It's a complicated problem. And as we'll see, what's important is to think about, okay, well, what does this mean for us, right? I mentioned with the last online lecture that this idea of, can we go back to normal? Can we start doing stuff to reverse this? Not the case. Okay? It's the idea that we just aren't able to get back to normal. Maybe we could have done that if we had gotten more serious about this decades prior, but we're just not there. So like you look at this model, the IPCC, the Intergovernmental Panel on Climate Change, I'll get into who they are in a moment, talk about some of their findings, but what they've done with all of their modeling of where we're going into the future, computer models that are predicting what will happen, even in the best case scenario. You can see this, again, it's that trend idea. We never actually dip back down, like below this red line right here. We never get back to the good old days. It's really a case of how much hotter, how much more will it suck in the future, right? Like it sucks right now. How much worse is it going to be as we continue on? This high is where we just say, you know what, to hell with it. Let's just do it. Everybody get a Hummer and drive it around the world and let's, keep burning coal and all that stuff. If we do nothing and we just continue to grow at the rate in which we do, life is going to get worse and worse and worse, right? And again, you can see this global average temperature, 64 to 68. You could say that's no big deal. But remember, we're dealing with mega climate stuff here. This doesn't mean this is what we're going to experience here in the Antelope Valley. There's going to be stuff worse than this, not as bad, all over the planet. It's going to mean a lot, like we'll see. I'll get into that. But so this is the worst case scenario. Best case scenario is where we're really, we're doing stuff. We're taking active measures to try to move, toward a less crappy future. I mean, that's where we're at, and that doesn't sound like a really good motivational speech here, like, make the changes today so life doesn't suck as much. But that's where we're at. That's the best we can do at this point. That's how severe this stuff is. And these climate models, it's important to realize too, these are complex things. I'm not going to dwell on this stuff, but there are a lot of variables that are brought into this, as well as constants. I mean, it's incredible what we're able to do with these computer models, how accurate we're able to predict what's going to happen, right? Whether it's in our daily weather. I mean, weather predictions today are incredible compared to what they were a decade or 2 decades ago. The computer modeling has gotten a lot better. And the same thing with these climate models. We can put in a lot of stuff. We can start playing around with pollution, as well as, changes in, deforestation and stuff like that, and get a sense of what will the future look like. All right. And so based on this, the IPCC, that Intergovernmental Panel on Climate Change, has figured out what the future is going to look like. And this is actually based on their initial 1999 work that they did. It's changed a little bit, but what I think is fascinating is, we go back 20 years. These were predictions. Today, this is reality. Okay. And so with the IPCC, This is a UN entity, and these are scientists who aren't actually trying to do new research. Instead, what they're doing is they're taking all of the existing research that has been going on with climate in general and bringing it together to try to get that big picture. What can we expect, right? Going into the near future, the distant future, and so on. And so they come together, every so often, and I think we're on our 5th report now or whatever, where they'll just kind of say, yeah, based on all these studies that are going on, here are the conclusions we can draw. And so this chart that I have here, I pull the very likely changes that the IPCC initially said would be taking place. Now, very likely doesn't sound very convincing, right? To say very likely sounds like, maybe, right? Like if I've had some of you actually emailing me like, are we going to be able to get through this? Am I going to be able to pass this class? Are we going to, finish the class or whatever? If I wrote back and said, yeah, very likely, chance that you could, pass this class and still graduate this year or whatever in light of all this coronavirus stuff, you wouldn't sound very convinced, right? But it very likely here means there's a 90% or greater probability that this will happen. And again, 90% might sound like, well, what about that other 10%? But honestly, when we're talking scientifically and statistically, when you say very likely with that 90% or greater probability, it means it's a sure thing, right? Like not technically it doesn't, but honestly, these are really good odds that it's going to take place. And we make decisions in our daily lives with, way less probability, way less odds than this kind of stuff, and we don't even think about it. So on it, just be aware. This IPCC, when they say very likely, it means it's going to happen, right? It's like there's no doubt that it won't happen because these are scientists. They still have to work in, variables and stuff like that. Like, one exception here could be if like an asteroid shoots out of the sky and knocks the Earth into, out of its revolution around the sun. And, then, this wouldn't happen because we'd all be dead. That's the other stuff that could happen, like really fluke stuff, right? So very likely means it's happening. And as I said, this is 20 years old now. This stuff is happening. Like it's proven to be true. Okay. But I want you guys to be aware of what is a sure thing, and to see that, we knew this was going to be the case 20 years ago. And of course we didn't do anything about it. And I know those of you who are 20 years old, in the class and hearing that, this is frustrating. This is, you might call bullshit on this because you had nothing to do with it, but here you are. So if that does frustrate you, well, hey, now's your chance to do something, right? To step forward here. So the IPCC, what they said was we're going to have higher maximum temperatures and more heat waves in continental areas. Okay? So let's break that down a little bit. So higher maximum temperatures means that our temperature records are going to keep going higher and higher. We're going to have, hotter days each summer where it's going to be, like a new record is set. And of course, we've been seeing that. If you follow along with the news and these stories, that's happening all over the world, right? So higher maximums, more heat waves, meaning consistently, hot days. Typically, we define it here. I don't know if it's a universal thing or what, but like a heat wave is usually when we have temperatures over 100 degrees for more than like 3 consecutive days. All right, so we're going to see more of those. Not only are our maximums going to be higher, but we're just going to have more consistently hot periods. And so what that means is we'll have more heat-related deaths and illnesses. Okay, and this is something like dying of heat is something we don't think about that often. It usually is because it affects the most impoverished of society, poor folks, the homeless, people who aren't able to go inside and turn on the air conditioning or just, go hang out in a movie theater or a mall or whatever during these hot periods of the day. It's people who have no way to escape this stuff, and that taxes the body, and people die, if not get, horrible heat stroke and some kind of illness from it, right? So we're going to see a lot more of that. We also see, this is the more impoverished, but this is also going to be a real issue too with people doing physical labor outside. Again, the kind of people who aren't usually at the top of society making the decisions, but anyone working out, in fields, doing construction, things like that. It's going to get more and more severe. We're going to see more people dying just because they're out working in July or August during these cases. And it's not good. I'll get to some numbers about how many people actually die from this every year. We'll also see, like with animals, heat stress there. What we can read into that is like, you got to watch your dog outside, make sure, he or she has enough water. But it also is referring to like livestock, right? Animals that we raise for food, they're going to be struggling. We're not going to have as many of those, survive, or they're not going to grow up to be as big or whatever. We can look at that as a cost of food going up, right? It's going to impact a meat-based diets. And you could say like, I'm a vegetarian, I don't have to worry about that. But that third bullet point, crops in general aren't going to be doing well. Plants aren't going to be doing well. All of this means when we have more heat waves and higher temperatures and all that, the cost of food is going to go up because it's going to be harder to produce this. And again, in continental areas where land heats and cools much more rapidly than bodies of water, right? So coastal locations won't see this quite as much. And of course, that's, more of that great class-based stuff that if you live on the coastal location, typically that means you're more wealthy anyway. You don't have to worry about it. The poorer folks live further inland. They're going to be faced with this stuff, right? And so, of course, this also means, and it gets into that positive feedback loop, as it gets hotter and hotter, we're going to want to, use more and more electricity to run air conditioning, as well as, keep our cars running. I see that like, going to pick up kids at school. There are, parents who will just park their car for like a good 40 minutes to get that good parking spot, and they just leave the car running the whole time to keep the air conditioning going so they don't get too hot and sweaty. All the time, they're putting more pollution up into the air, adding to our little greenhouse blanket, and, making it worse and worse and worse, right? So that's the higher maximum temps. We'll also see it's going to shift in the winter as well, where we're going to have higher minimum temperatures. So winters aren't going to get quite as cold, right? And we're going to see fewer cold waves. So that with the last lecture, that little cartoon with the stick figures, talking about the fact that these cold waves used to be more normal. They freak us out now, all because we're just not used to them, because they don't happen as much. Now, the good news is, when it's cold, that kills people too. So we're going to see less of this if we don't have, freezes specifically, really, really cold periods here. So that's good, there. Crops and livestock as well will do better. So we won't have these frosts that, wipe out plants and damage them. The problem, though, is that having these cold winters, they've been a nice barrier up here in the mid-latitudes from tropical diseases and pests and stuff like that. So there are certain things we've never had to worry about up here in North America that they do have to worry about, down near the equator and in the tropics, because it's just too cold and stuff can't live that long. So it's the concern is, as we don't have as many freezes taking place, we'll start to see the northern migration or poleward migration of some of this stuff. And in fact, we have seen that. And then also, the one other good thing here is that we won't have to use as much energy for heating. So like that stuff, sounds okay. But any benefits there are going to be lost with all the heat-related stuff that we already discussed, right? Let alone the spread of disease and all of that. And I can say, like, the whole coronavirus, COVID-19 concern that we have, there's no indication that this is as bad and nasty as it is because of climate change, because it's not as cold right now as it usually is or whatever. So that's not, a guaranteed thing. We don't want to make leaps toward that. What will be interesting is in a couple of years, we'll start to see the results of scientific studies that maybe have looked at this stuff. Maybe we'll see there's some connection between climate change and this specific disease, but nobody at this point, if anybody says it's definitely connected or an example of this, they're lying or they don't know what they're talking about or whatever. We need to do the studies to make sure it's, A plus B equals C, right? So that's not exactly what we're talking about necessarily. And then finally here, more high intensity precipitation events. Okay, so it's the idea that we're going to have rain primarily is what we're looking at here, whether it's a case of hurricanes, whether it's just thunderstorms or whatever, but we're going to get a lot more rain quicker, right? In one, fell swoop. And what this doesn't get into here, but we know is also the case, is we'll have areas where we have more drought, where you're not getting any rain. But then when you do get rain, we'll have these more high-intensity precipitation events, which leads to flooding, landslides, soil erosion, all sorts of stuff, right? And this goes back to the hurricane idea that we are seeing. It's no longer a prediction, but it's the case of warmer ocean temperatures are leading to the formation of these really intense hurricanes, and it's happening at a rate that we haven't seen in the past. When, a Category 5 hurricane was a once-in-a-lifetime event in like the Gulf Coast or whatever, this is happening a lot more frequently, right? That's the big concern, and that costs billions of dollars to repair, let alone, the lives lost, and just, the economy disrupted and all of that. So these are all things that the IPCC initially said were going to happen, and sure enough, they're all happening. This is the reality right now. Now, the problem I see with a lot of this stuff is that we still don't take it seriously. Like the heat thing doesn't freak people out as much as it should be, right? And to put this into perspective, I like to compare it to something else that we've devoted a lot of our money and attention to. In the past, it's looking at terrorism and preventing this stuff. So I have some numbers here. So since 9/11, all right, September 11th, 2001, 233 people have died from terrorist attacks. And sure, if you put in 9/11, you increase that number significantly. But what I'm looking at is like what we've done since then to address this stuff, right? And this is not to belittle terrorist attacks. It's not to make fun of people who have lost folks here or whatever. No, this is clearly a bad thing. I mean, I do point out about half of these are from non-Muslims. This isn't one group of brown people are doing all this stuff. That's important to know in there. But honestly, if, here in the United States, your chances of dying from a terrorist, from some kind of terrorist attack, very slim when we compare it to this climate change related stuff, right? 2,356 people have died. It's a rate of 124 per year from heat related deaths. Okay. So again, since 9/11, much more likely to die from heat than from a terrorist attack. Okay. And hurricanes, again, going to just one example of, increased precipitation, high intensity precipitation events. But tornadoes and other stuff can fit in here too. But officially, we lose about 60 people per year. Now that's official. We look at Puerto Rico, which technically is part of the U.S. Some people learn that for the first time with Hurricane Maria. But it's looking at estimates are like 3,000 people at least died from that one bad event, right? Not officially, but it's the people who are actually there on the ground and studying this stuff, seeing that the deaths related to this hurricane way higher, right? So way more likely to die from climate change related activities than terrorism, right? But, in these past 20 years, roughly, we have the IPCC things we know about climate change. We ignore that, willfully ignore that in this country. And sure, 9/11 shocks a lot of people, freaks a lot of people out. We are scared as a nation. We want to invest in this stuff, but we quickly realize that these billions, if not trillions of dollars we're spending just to stop terrorism alone, we're throwing it away, right? And we're throwing it away when honestly, we don't even need to worry about it that much. And the pictures I have here, like that one on the top, what is that we're looking at? Some of you guys have gone through that, right? It's a body scanner you'd find at an airport. I've got these in Burbank or LAX or whatever. In fact, homework assignment. If you haven't gone through one of these, just go buy a plane ticket. I don't care where you're going to. Don't even go there. But just go through security. Oh, so much fun to get diverted into the body scanner. You go into this like phone booth kind of thing. Not that most of you even know what a phone booth is, I guess, at this point. But still, you go into this little cell right here, like this guy in the red shirt is doing, and you put your hands up so it doesn't confuse the machine, and it swirls around you, just like a clonk, 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 and it does this full body scan. I don't know if you guys have seen what these things can see. In fact, if you're looking for a good time, do a Google image search of body scan images or whatever. Oh, it's better than porn. It's amazing what detail these things are able to get, how your genitalia are perfectly reconstructed without your clothes ever coming off. I mean, it is the creepiest thing in the world. And what they did, and when they first put these things into place, is the TSA agent who was seeing these images was right there next to you, right? So you're standing there. They take this, naked picture of you without your clothes ever coming off, and that one person is just there looking at you naked and looking at you right there, and that was creepy as hell. So they moved that person into another room, at least, which actually might be creepier, right? Because we have no idea who's looking at us or what's happening right there, but they have this stuff far away. But even that, with this incredible technology that isn't cheap at all, and of course, who's paying for it, right? We are in one form or another, whether it's through just taxes in general, whether it's through increased cost to fly on a plane or like whatever. This isn't, nobody is taking the hit here, from the airlines or these different companies. No, this is getting passed on to us. So it's incredibly expensive. But we also find every year there are results of like the FBI sneaking stuff onto planes. Like even with this technology, we're still able to, get weapons onto planes do, all the same terrorist stuff. And so like the FBI or whoever will check this to kind of see how the system's going. And when these results get released, you can see that all of this really expensive stuff, it's not helping at all. This isn't what's preventing more terrorist attacks. It's ridiculous, but billions, if not trillions of dollars goes into keeping us safe in a way that isn't necessarily the best way to keep Americans safe. Yet when it comes time to helping people not die from heat, we get stuff like this down here at the bottom, these cooling centers that show up, which are just the saddest things in the world, where we just open up some big room, we turn on the AC, and we let poor people and old folks come in there and just sit and cool down. And then we're shocked that people don't want to just sit in this room for 8 hours a day with nothing to do in this place, right? That's what we do. And we still have, there's more people dying from this stuff. The hurricane stuff as well. We're not really taking steps to deal with this, to move people out of harm's way or anything like that. No, we're rebuilding. We're spending billions of dollars to rebuild these different cities. And we know this stuff is just going to continue to happen year after year. What we need to do is to be a lot smarter about how we're trying to make the future not suck as much as it possibly could, right? And so just playing the odds here. This is showing, I pulled this out, looking, again, comparing terrorism to like heat waves. You can see, a 1 in 10,000 chance of dying from a heat wave compared to a 1 in 45,000 chance in dying from a foreign-born terrorist, right, here in the United States. And then this also looking at, refugees and illegal immigrants and all that. That's also fun to look at to see what a, ridiculous thought that is, that illegal immigrants are going to, cause all of this trouble. It's not how it works. And of course, really, with a lot of this stuff too, this is scary, but it's also like right now, where was it here? I was looking at like influenza, pneumonia, 1 in 70, right? And it's not the COVID-19 is not the same as the flu, but it is, pneumonia is one of the things that's leading to people dying from it. That's also a terrifying thing. There's a discussion for another moment in time, but that's something to think about too, right? Like right now, this is what we're all scared about, but still, what I'm going to argue for is this is the stuff that long term we need to be thinking about. We need to be aware of. That's the concern that we should have. Okay, now that alone, though, that's just what the IPCC has said is going to happen. Okay, we also know that other stuff has been happening. Wasn't part of that initial IPCC very likely to happen, but it's worth talking about right now. Again, because we know it's happening, but also with some of this stuff, we know that it's not necessarily what we even expect to happen, or the results or the impacts won't necessarily be what we're thinking about. So I'm going to talk about these three things: sea level rise, polar sea ice melting, and habitat loss. And I want to cover those, not, explain what they are, why they're happening, but also get into what does that really mean? Because I think that's the really important thing to think about here. So sea level rise. All right, so we have, and these statistics are, again, it's that mega climate kind of scale, global scale stuff. But you can see seas predicted to rise roughly 1 foot to 1.5 feet by the year 2100. Now that alone might not even sound that scary. This picture, this was from an old textbook I used to use. It just cracked me up because they show this with sea level rise, and it just, like, the picture, clearly this is like some storm surge from a hurricane or whatever, but it makes it look like these people were just like they're trying to get to the house, but the ocean overtook it and they can never go back there again, right? Like the lady's just pointing out, like, yep, used to live over there, can't get there anymore because of the sea level. Is not quite that simple. And actually that's a problem, is our way to think about that is you just, like, if we go back here where it's showing, where the sea level will be, like how much beach we'll lose. I mean, that's not catastrophic. It's not like we have people living right here that are going to die. We've not done a good job of explaining why this is a problem. All right, and I've tried to do this with students. This is an example, an artist put together what this kind of sea level rise means for different cities around the world. I, of course, picked Venice, California. It's a fantastic place. I mean, it's still good. It's getting a little too clean. God, but Venice, like back in the 90s, so skanky and gross. Like you could just like look at it and you'd get hepatitis or whatever. Like love it. So you're telling me that Venice could be wiped out, could be like disinfected by the ocean, and my kids don't have a chance to go here and pick up diseases and get tattooed and whatever? Like, no, I don't want to live in that world. So let's see what the future holds. So this is it today. We've got the map here, this planimetric view, just kind of showing where the water is and the roads and all this stuff. And this is just to kind of make it look more realistic for us, right? So here it is today. 100 years. Did you see what happened? Look at that. Dun dun dun. Did you not get? Look at that. All those cyclists dead, right? Just washed out into the ocean in 100 years. Okay, yeah, it's kind of stupid. When you look at like this lady right here, still walking, still trying to walk in 100 years. But what it's showing is, okay, the water's up here. But honestly, what that's showing you is that, yeah, life in Venice, not a big deal. How does this make me want to go out and buy a Prius or, recycle more or switch to solar energy or whatever, when this is the scary reality, right, of what's going to happen? Now you can see down here, like with the actual Venice system of little canals and all that stuff, that will flood these lower areas. But still, this picture, it's not doing much for me. Now we can look further into the future. This is a little more intense, but look at the date, right? The year 2300. Like that is so futuristic, right? I mean, that's in 300 years. Yeah, that's unfortunate. We don't even know if the United States will still exist, to be perfectly honest, in that point in the future. And then this gets really hardcore right here, the year 2400, and it does kind of look like the water's going up everywhere, but actually it's here, right? And we see the trees are still poking through. So that's significant for Venice. But the other thing that we never discuss is the fact that, like, especially now that really wealthy people are taking over Venice and, you know, buying property and stuff like that, these people aren't going to sit around and just let this take place. They will build up seawalls, and we see this happening in places like New York is doing it, San Francisco is doing it. We see, an investment in these wealthier areas in building up seawalls to keep the ocean, out of the land, right? So wealthy places are going to be able to deal with that anyway, and Venice will be totally fine in the year 2400, assuming that, our current system of government and economy and all this stuff is continuing on to that point in time. This isn't what we need to be freaked out about. Okay? Again, what we need to be concerned with, as I mentioned before, is that as sea levels get up higher, it's going to affect hurricane-prone areas in a much more significant way. Whereas that hurricane is coming from the ocean up towards land, it has what's called a storm surge, where it's pulling the ocean water up with it, and so it brings water onto land, and we have significant flooding. And so with these ocean levels even higher, even just a little bit higher, say like a foot, that can mean, huge catastrophic damage with these storm surges that come with these, higher intensity hurricanes. Okay, that's the thing. It's not that we're going to have to just abandon cities, year round. It's that the flooding events are going to be much more significant, which is going to wipe out coastal cities, wipe out farmland, stuff like that, right? Really disrupt human life. And sadly, the poorer places around the world that are coastal are going to suffer from this much more than the wealthier places. And the reason why the wealthier places are wealthy in the first place is because they benefited from the technologies that have in fact led to this climate change. So just from a justice standpoint, it's completely unfair. And that's something we need to think about, ethically, morally, even. What are we, what's our role in helping out some of these poorer nations that are faced with this stuff right now? That's what we've got to be thinking about. And we'll talk about more of that stuff later on in the semester, I'm sure. Okay, so and here. So this is, the storm surge idea. This is the reality. This is what rising sea levels is already doing. The water is coming on. It's destroying coastal communities. And then the water eventually goes away, but it's caused damage, right, already. So it's not this that we're worried about. It's this. Okay, that's what increased sea level and the sea level rise actually means for the United States as well as the world. All right, now let's get into this polar sea ice melting, which is referring to what we're really looking at is the North Pole. Okay, and so at the North Pole, there's no actual land mass there. There's no continent at the exact North Pole. It's an ocean. It's the Arctic Ocean, but it's also frozen. And so the North Pole is it's been frozen, forever. And it's what we call sea ice. So it's not glacial ice, because glacial stuff is up on land. So like here in Greenland, this is a glacier, but this sea ice out here, it's frozen water. Okay. So polar sea ice, that's what we're dealing with. And we have natural fluctuations. So March here, this is the end of winter. This is our sea ice extent, maximum extent, where we have, a lot of stuff is frozen shut, right? September will be the end of the summer. We have a reduction, right? This is our minimum sea ice extent. And so it's still covering the North Pole itself, but it doesn't stretch out as far as it could. But honestly, with this, even though we have natural fluctuations, it's been a lot of ice. Historically speaking, we haven't been able to take a ship say from over here, in Europe, we're looking at the British Isles and Scandinavia over here. We couldn't go from Northern Europe and sail over here. Here's Siberia. Here's Alaska. We can't go from the Atlantic basically to the Pacific via the Arctic simply because it's been completely frozen, because you couldn't have enough water flowing through to take a boat, right, from one side to the other. Okay? But what we've seen is that it has been melting. And in fact, to go back real quick, I said we haven't been able to do that. It was like 2012 when we actually first did it, right? So the new reality is actually we can do it at this point in time. That's pretty alarming. But then you get stuff like this, and this is stuff I really get excited about. So we have our news duck right here saying, mainstream media, how are you covering the news that Arctic sea ice increased by 60% this year over 2012? And the news, the evil media, look at that, those evil eyes, says, predictably, Mallard, even as we speak, we have assigned more than 3,000 of our best reporters to ignore these data as energetically as possible. All right, we're gonna ignore the fact that the sea ice is increasing, that it's actually colder, that we're getting more stuff coming in. And so I saw this. I was like reading the newspaper, having my coffee before coming in to teach, back in 2013. And I saw this. I spit my coffee out and said, what? No one told me about this. What's going on? And luckily, there's an asterisk right here for reason.com. So like any good, man of science, I went to the internet and looked this up and found out what this guy's referring to is this right here. Okay, so this is from JAXA, which is a Japanese agency. They're like our NASA over here. A lot of advanced nations have these scientific things. Whenever I say JAXA is like the Japanese NASA, people always laugh and giggle. I don't know why. Maybe it's because it just sounds funny. Whatever. But yeah, we're not the only people who study this stuff. And so the Japanese agency here has done a lot of research on looking at this Arctic sea ice extent, the maximums and the minimums, and that's what we're seeing. So down here at the bottom, we've got January through December, right? So up here, where we've got this higher value, so it's the sea ice extent. So this is more sea ice here, less sea ice down here. This is in the winter when it's naturally colder because it's the winter, right? So more stuff freezes. So we have more sea ice up here. And then the year progresses, right? We go into the summer. It warms up, even though it's still incredibly cold up there. It's warmer at this point in the year. So we see a natural melting of this sea ice. There's less of it around, right? But what we're seeing with this chart is how that's changed. This lightest gray little dotted line here, that's the 1980s average. And so because it's easier to see, and this is actually the more important stuff right here, we'll just focus on this spot. So you can see in the 1980s, this was the average in terms of the least amount of sea ice after summer, right? In September. That's what we were dealing with, right? And then the 1990s, this was the average, and you can see it's less than the 1980s. So we're again, it's that trend idea, right? Less sea ice. This is the early 2000s, that first decade. That's our average, significantly less when we're looking at that. So it's dropping down. And then we have these different, specific years. So 2007 was the record for the lowest amount of sea ice, this kind of greenish, ugly green color here. 2007 was the worst year. And then that was beat by 2012, okay, which is this orange thing. We've never seen anything this bad since. So that was the worst year ever. 2013, that next year in the red, and this was actually taken, you can see it's not even through, this was in 2013 itself, but you can see not as bad as 2012, huh? So if we go back here, that increased by 60%. They're referring to the fact that, yes, compared to the worst year ever, it was better. We did see an increase. But the reason why the mainstream media didn't have this, hooray, we defeated climate change story or whatever, that it's a hoax or whatever, is because this is still awful, right? Even though it's an increase, it's not good. It's not good news. Now, if this red line were up here, if we had a maximum or a minimum amount that was actually better than what we saw in the 80s or something, that's worthy of, at least some mention in the news. And of course, we'd want to see, is that a fluke? Is it going to keep coming back or whatever? But no, it's not some conspiracy by the media. It's the fact that if you can actually read a chart, you realize that, oh yeah, this is still awful. Good. We're not in this, awful apocalyptic stuff here, but we're still not better than what, the previous decade had shown or anything. This is still terrible, right? So that's what we need to look at. And sure enough, this is 2013. You continue forward with other years. We're still, 2012 was the worst, but in more, recent years, this one's from 2016, still bad, right? So this was clearly a fluke in the sense that it was, more ice had melted than any other year. This is more of a normal thing, but still, this reality down here, it's going to show that we're still losing ice. It's still worse than it has been. All right. Now, what you could also ask is like, well, who cares about sea ice? So there's not as much ice there. Ooh. Yeah, I get it. It's kind of like, what's in it for me kind of thing. And so this is showing, and a lot of these things, these are older maps and stuff I've shown. Some of these statistics might be out of date at this point. But this one showing how, kind of 2000, this is what it looked like for that minimum extent, right? So where it had melted, again, in, September, this was the least amount of sea ice we had there. By 2050, it's going to get less. And by the year 2100, we'll hardly have any, right? That's the idea. And eventually get to the point where there's just no sea ice anymore because temperatures don't allow for it. All right, that's the idea. So eventually we're going to get to where the Arctic is just open water. And so you could say, like, who cares? We should all care about this. This is serious, and not just from like a, habitat standpoint or ecosystem standpoint, but from a geopolitics standpoint. Because right now, we've got ice all over the place. But you know what's underneath that ice? Yeah, water. Okay. But you know what's underneath that water? Sure, ocean floor. Okay. But you know what happens when you dig deep into that ocean water or that ocean floor and you go deep into the earth there? You know what we find? Give you a hint. It's wonderful. It's our favorite thing. As Americans, what do we love more than anything? Oil. Right? There's all this oil, this untapped oil underneath the Arctic Ocean. And we haven't been able to get to it because of this stupid ice. But hey, no ice, we get more oil. It's fantastic, right? And sure, that'll lead to, ridiculous temperatures and, hurricanes and all this stuff. But still, we can drive our awesome cars and, kind of have life as normal. Fly around the world and do all that great stuff, right? Yeah, and we get it. We get some of this oil because we own Alaska. Yeah, we touch it, so it's ours, right? That's how grown-ups operate. Because we touch with our land, this is technically the United States, we get us some oil. Now, Canada, sure, they touch more of it. It's Canada. What are they going to do? We're going to say, can we have some oil, please? They'll say, oh, sure. Not a problem there. Greenland, nobody lives there. And this is, also why I'm talking about everybody made fun of Trump for wanting to buy Greenland. It's actually not the stupidest idea. We'll talk about that. But it, they have it technically, the Danes get some of this stuff. Scandinavia, no big deal. But, who's this? Over here. Who operates right there? The Russians, right? The enemy. And that was the thing. See, I'm an old man. I remember the Cold War and how evil the Russians were, the Soviets, and you kids today. Luckily, we're getting back to the point in time where we know the Soviets are still there, just waiting to strike. We see people freaked out about the Cold War. But here's the reality, is that as this opens up, there's a lot of concern that wars are going to be fought here in the Arctic over this precious resource, right? The days of, Middle East a battle and stuff like that will seem like this quaint, far off thing, that we're going to be going to war with Russia in the Arctic over this oil. And that sounds crazy. I know. I say stuff like this to my wife and she just gives me that look. But here's the deal. And here is the greatest / scariest thing ever. As I was, saying this stuff for years. And then the news media, the evil mainstream media, they start kind of showing that, oh, this isn't quite as crazy, right? This is from 2015, where we have Russia as well as the United States are investing more in Arctic warfare, right? Submarines and ice-breaking vessels and stuff like that to be able to battle in these much colder areas. And of course, why is that? Because of that oil, because of this new, and trade routes and stuff like that as well. As the Arctic Ocean opens up, that's significant. And we see it everywhere. There's all sorts of this stuff. This is the kind of stuff that climate change is really doing or going to be doing. This is the kind of stuff we need to be concerned with is going to war in new places and desperately trying to get resources to keep life as normal as possible for our country at the expense of other countries and all of that, right? And it would be nice to think, like, as we get to a point where the climate is changing, where life is collapsing around us, we can come together as a globe and, forget this nationalism. We work together as humans to thrive. No, we're gonna buy more, tanks and stuff, blow up stuff. Special boats that can blow up stuff in the ice and all that. That's something to think about. And that's should be a concern, because also, this war is kind of much closer to home than some of these very foreign things that we have going on in, Afghanistan, Syria, Iraq, wherever around the world. Those seem very foreign. This will be much closer. Okay, well, that was dark. Let's talk about something less concerning, right? Like how all the animals are going to die. So the third thing that we're going to cover is what we call habitat loss. Although I'm going to say, while most people say habitat loss, we should say habitat change. Because it's not necessarily a loss straight across the board. But we'll see stuff like this. Look at the coral reefs. They're dying. They're bleaching. They're not as bright and vibrant anymore. And all of that. And that has to do with changes in the chemistry of the ocean, changes in the temperature. Storm surges as well are moving water away. As that's happening and it's exposing these things. And the coral's dying. Doesn't that freak you out? Isn't that way worse than war with Russia? No? Yeah, nobody. I mean, yeah. We can say here in, again, here in Southern California, we can go, oh, the coral, that's a shame. But that doesn't, call us to action or whatever. It is kind of an abstract thought for a lot of folks who don't live anywhere near these coral reefs, who aren't scuba divers or whatever. But I mean, that's an example of changes in climate, of course, are going to lead to changes in habitats and where organisms can live. Now this one, when we talk about the mammals, this is sad. Look at that poor polar bear right there. Look at that. Yeah, and so a polar bear it's a maritime mammal, meaning it spends most of its time out in the water. It swims around, but it's not like a whale or whatever. It doesn't stay in the ocean all the time. It's still a bear. So it finds like sea ice to go hang out on. It'll swim for a little bit, hang out on the sea ice. It'll use that as a platform to, capture seals or whatever. But as more sea ice melts, these things have, less habitat, right? And that's, everybody's, oh, the polar bear. Look, it's a bear, right? And we all know the bears are evil. And frankly, I'm not even totally convinced that polar bears even exist. I've never seen one in the wild. I mean, yeah, I've seen them at zoos, but that could just be a brown bear that's painted white or whatever. But honestly, it's a bear. Do you want a bear living in your neighborhood? No, you do not. Pop quiz, what do we have on our California flag? It's right, a bear. What kind of bear? Brown bear, a grizzly. Do we have grizzlies in the wild here in California anymore? No, we don't. We shot the last one, I want to say it was like 1920, when we shot the last grizzly bear here in California. And was that a sad day? Absolutely not. Everybody high-fived, like, yay, we finally got rid of them. Because grizzly bears are terrifying death machines. And now people say, like, we should reintroduce the grizzly bear. But they're scary as hell. They're bears. So this, you could look at this as like, oh, we lose polar bears. Yeah, good. Good riddance. All right, one less thing to kill me out in nature. All right, the corals, I'll let them stay. We'll try to help them because they've never killed me, or people like me or whatever. But bears, to hell with them. Right? Are you with me? Yeah, I'm very sincere right now. But here's the deal. Here's why this isn't working out for us. I would love to say that, like, good news, polar bears are dead. We're safe, right? Take your kayaks out into the Arctic. You won't be killed. No, that's not the case at all. Instead, the bears are conspiring against us. And let me explain what I mean here. So, I don't know if you guys are aware, but you can actually legally hunt polar bears, right? Even any like endangered species, there's still cases where they're hunted to manage populations and stuff like that. And honestly, to go hunt polar bears, it's a very expensive process. It's like thousands of dollars to get a permit. That goes towards indigenous people up in the Arctic, to help them out. And they'll guide hunters, out onto the ice to find these things. And so there was a guy, an American guy, he was like from Montana or something like that, and he saved up the money, got his permit, went out, this is a few years back, went out with some, indigenous folks, Inuit, Eskimo, I don't know exactly who, but went out onto the ice, and they saw that white bear off in the distance, and he holds up his rifle and he aims and he shoots it, and sure enough the bear dies, falls over dead, and they high-five and they start walking closer to the kill to get that trophy. And as they walk closer, they realize something's not quite right. I mean, yeah, it's a bear and it's dead, but it's no polar bear, right? I mean, it's primarily white, but as they get closer, they see the paws are a little darker, and it's got these like dark circles around its eyes, and the shape is just kind of off. And they realize, oh my God, it's not a polar bear, it's a grizzly bear. Yeah, half polar bear, half grizzly bear, grizzly bear. I'm not making this up, people. This is a real thing, right? And so this guy shoots it, and ironically, like, that's the only way we knew it even existed, right? A lot of people said, like, well, great, grizzly bears exist, and you just killed it. And the hunter said, hey, look, don't get mad at me. If I hadn't killed this thing, you wouldn't have known they existed, right? Well played, hunter. But yeah, it's the idea that you have grizzly bears, which are not ranging up where we have the polar bears. It's too cold for them, so you'll see grizzly bears in Canada and Alaska, and they'll roam around there. But as temperatures get warmer, they can go further north, right? And so you picture some grizzly bear cruising around up north, and off in the distance, he spots some blonde, right? And one thing leads to another. They get to talking, they have a little baby, and a grizzly bear is born, which is really, I'm going to say, is the most terrifying bear possible, right? Because grizzly bears are killing machines from land. Polar bears are killing machines from the sea. They can kill you, in two places, right? If you have a grizzly bear, like have sex with a pterodactyl or whatever, we're all dead. We're never safe ever again. So luckily, the guy killed the grizzly bear. And we found a few more, actually. It's always hunters killed him. I don't think we've ever found one just like out in the wild and not shot it dead right there. But these things exist. And so what I'm saying here, like, okay, I'm not really afraid of grizzly bears attacking me in my sleep or in the pool or whatever. I don't really want bears to die. But what this goes to show is that habitat loss it's not as simple as that, right? What we're going to see is change in every sense of the word. That yes, we'll have some species that cannot continue to exist in the same locations. That will lead to migration for some of them. That'll also lead to adaptation for other things and these bizarre hybrids that will show up, right? The future, it doesn't mean that the future is like mass extinctions galore, although it is pretty clear that that is going to happen with certain species. They're not going to be able to survive if this stuff gets worse and worse and worse. But it means really that nature is just, it's going to get crazy, right? It's going to be in a situation where we're not going to recognize it. And that's kind of the whole idea with this new concept of the Anthropocene. It's that what we've taken for granted as natural isn't natural anymore. That you could even say this Pizzly bear is not a natural thing because it's the result of human activity, right? We're the reason why these could even begin to exist as temperatures go up. This is crazy, crazy stuff. And it is tragic in many cases that just what has been a beautiful part of nature is changing. Okay? Nature's not going away, but it's not going to be the nature we're used to. That's a big point of this. And another thing to think about too, we're talking about habitat loss, and this is showing the darker the color, the more significant it will be. Of course, we see a lot of this significance up in the Arctic region where temperatures are going to get warmer. Not, necessarily it's always the case there. But that's going to happen to Arctic creatures. But at the same time, it's important to remember that we humans we're part of this ecosystem. We're part of this planet. Our cities, our habitats are going to suffer from this habitat loss as well. Right? And this is showing the city vulnerable to sea level rise. That gets back into the idea of storm surges, okay? Hurricanes. The fact that these three cities here, vulnerable. We don't see Venice, California mentioned because honestly, that's not our greatest concern. We're more worried about, drought and fire over here. But here it's where we have those storm surges. But we're an incredibly wealthy nation. We can pay, for preventative stuff. We can rebuild and things like that. But other parts of the world, not so well off, right? And so that's another concern. And you can take it from just a humanitarian standpoint that we don't want to see other humans suffer, which some of you will go like, yes, I agree with that. Others, you know who you are, will be saying like, I don't really care about what happens in Jakarta because you're not Indonesian and don't know anybody over there or whatever. And ignore that. But honestly, it also gets back to this idea of global security, right? If you have cities that are being decimated by climate change, their economy is suffering more and more and more. What is that going to, lead to in terms of, issues of terrorism and instability and things like that? Or as well as, human costs, new diseases and stuff starting there and then spreading and able to come here because we're just not, having these freezes as much. I mean, all of this stuff is connected. Humans are not immune from these things. So when we say habitat loss, it's habitat change. And also we need to realize that we are part of these habitats. We're connected to this stuff. So yeah, temperatures are going to go up. Ice is going to melt. Polar bears are going to suffer. But humans are going to feel the impacts, in ways that we're starting to see, but in other ways that we haven't even begun to comprehend. Yay! I know, it's depressing. Quick, Google, puppies, puppy videos, real quick. Go to YouTube, watch that stuff so you're not super depressed. It's depressing. There's no sugarcoating that. The future is scary. But again, it's a case of, what we need to do is come together to figure out how to deal with this stuff. As I said in my previous lecture, it's not a case of individual choice is going to save the earth. It's working together as, an entire nation, as multiple nations working together globally. We were able to do this with the ozone layer. We were able to come together, across the planet and, make the stand and say, we're not going to let the ozone layer be destroyed. We did it. It's not fixed perfectly yet, but we stopped the damage from getting worse, right? Climate change, we've been awful about this stuff, and we need to start thinking about it from a very practical standpoint. And the only way we're going to do that is to get involved politically, right? And that also doesn't mean, that one side, if we look at our two-party system here, the Republicans and the Democrats, one side, they're the good guys, the other side are the bad guys. To be perfectly honest, both sides have been terrible about addressing this stuff in a very realistic way. So in order for us to fix this, if you don't want life to suck quite as much, we got to get active. We got to be paying attention to what's going on here, what we can do to actually enact this change, but it's up to us to do it, to not be apathetic, to not just go like, well, I've had a good run, right? So there, we can make this not suck as much. It's possible. This is what California has to face. It's going to get drier. Remember our good dust storm from 2012, 2013, whatever it was. We'll see more of that. Get politically active, right? To getting it. I've already talked about like water storage and dealing with just smarter water policy in general. These are the things we can do to make life not suck quite as much, as well as looking at new forms of transportation and investing in better forms of energy and these kinds of things. But we got to take the time to pay attention to this stuff, go through the nerdy stuff, right? And the boring stuff, and not be distracted by the sexy things that do distract us, but actually focus on this kind of policy. Not going to be easy, but here's your other scenario. You can continue to ignore it, and I guess go ahead, continue to ignore it. Just make sure you invest in a really in a bitchin' car or whatever, because this is our other possibility, right? And while I'm not gonna lie, I'm kind of torn between which reality could be the fun one. I'm getting too old to do this kind of stuff, so I'm gonna pay attention to the policy. All right, there you go. There's climate change. It's something we should be talking the whole semester about, and we'll come back to talking about it in future lectures and stuff like that. But there's a general idea of the science and what we can expect, and that's what I want you guys to focus on here. Now, the reality is, I would be saying, hey, next time you come into class, we're going to have our tests and our scantrons and all of that, and be ready, and you're going to be writing about climate change. That would be your big 20-point question at the end to explain what is climate change, how is it working, explaining the greenhouse effect, being able to talk about what's going to happen too, all this IPCC stuff I just covered, talking about this other stuff like habitat change and that kind of stuff, right? The reality is we're not coming back to campus anytime soon, so I'm putting together your second exam in Canvas. Okay, so it's going to be an online test, which sucks. And you might be thinking like, sweet, right? I can take it at home, and that means I can have my book and my notes and the internet and all this stuff. But look, it's the same test I'd be giving you in class. It's the same amount of time. In fact, I'll probably round it to 90 minutes instead of the 80 minutes we usually have. But one thing that students realize, like I've done this in other classes where I've switched to an online version of a midterm or a final or whatever, as you go into it thinking that, okay, cool, I don't have to study at all because I can just Google stuff and whatever. And those students fail spectacularly, right? Where they get like a 30 out of 100 or whatever, because you go in with no knowledge whatsoever, figuring you can fake it as you go. But in the time it takes you to start Googling questions and look stuff up, it's not going to work out. You're not going to teach this stuff, to yourself. And these are questions I've written, which means that as if you type in the exact thing into Google, you're not necessarily going to get anything that's actually helpful. Or you might get, in some cases, I've found in testing this in other classes, I don't know if it's professors who do this or whatever, but I've seen places where it's posted where you Google and you get the wrong answer that pops up right off the bat, which I love. So like, I get it. Nobody's watching you. You can do whatever. It's technically going to be an open note test, but if you don't study ahead of time, if you don't have those notes carefully looked over and organized and cataloged, indexed, whatever, you're going to fail the test. It's just as simple as that. Okay, so once this is done, I'll post it. I'll make an announcement in Canvas, explain some key stuff. But when you're ready to take it, remember that it's going to be timed. All right, you get 90 minutes to take this thing, which is plenty of time to take it. But if you don't know what you're doing, if you're not focused, it's going to go by way too quickly and you're not going to do well. All right, so be prepared before you take it. And I'll put it up because we have this chaos going on. I'm not going to make you guys take it, on the day of your class would normally meet, or I'm not only going to give you like a 1 hour window or 2 hour window or whatever to do it. I'll give you a couple of days, right? Once you start it, that clock will start ticking, right? 90 minutes will go past, from that moment. So you can't start it and stop it and all of that, but I'll give you a few days. So if you're dealing with kids at home, which I know I am, and it's killing me. But if you're dealing with homeschooling now, or even just babysitting in general, or if you're still at work or work's gotten weird, or like whatever it might be, I'll give you enough time so you can take it, whenever during that window. Just remember, you only have the 90 minutes when you press begin or start or whatever. Okay, and again, it'll be the same deal. There'll be an image of the hydrologic cycle. You'll answer questions about that. There'll be that true, false, multiple choice stuff. Take your time with it. And then you will be writing about climate change. There'll be a spot in there where you'll explain climate change to me. I've said a lot of stuff about this. Your book chapter gets into even more detail in this stuff. Be prepared to give me a lot, right? Convince me you know exactly what's going on, what's happening. Don't try to fake this. Don't try to BS this stuff. As you do it, because it'll be obvious. I'm going to be asking specific questions. Make sure you have those specific answers. All right. So this will show up soon, this test, and we'll finish this. And we've got this kind of extended break, like a 2-week spring break, I guess, coming up here. Honestly, I'll still keep posting stuff. I won't expect anything due during this break period. But the reality is, we can't really necessarily take vacation if our whole lives have been thrown out of whack. So I'll just keep posting stuff, and you guys can, get to it when you get to it, right? And as always, some of you guys have been doing this. Communicate with me. If you have any questions about any of this stuff, send me an email. That right now is the easiest way to get a hold of me. I'm trying to check this stuff throughout the day so I can get back to you as quickly as possible. And if you haven't heard from me, if you communicated with me, haven't heard from me, send me another email, because maybe I missed it. But I'm really trying to make sure I'm in communication with you guys about whatever. Specific questions on the material. If you're just kind of freaking out in general, you just need another human to be able to communicate with. Who isn't your immediate family, send me an email. I'll let you know whatever it is you need to know. All right? All right. Well, there you go. Climate change. Life is going to suck in the future. It doesn't have to suck quite so much if we actually get our asses in gear. All right. Pep talk over. Have a lovely rest of your day or evening or whatever. Stay safe, and I'll talk to you later.